Very good morning to one and of all. So today we are going to discuss about stationarity and distribution and density functions. So as we know that the meaning of the stationarity is that if all the statistical properties of a random process do not change with the time, and this is the basic meaning of stationarity. And let us consider if all the statistical properties of a random process are varied with the time, then they are going to be treated as non-stationarity processes, right? So now we know what do you mean by density and distribution functions for a random variable. Now we are going to see the distribution and density functions for a random process. So see here. So this is the formula of a random process x of t for the distribution function. So here, why we are going to mention the distribution function and density functions in the sense these two are very useful to us in order to find out stationarity, right? So previously we discussed about the meaning of stationarity, and see, let us consider a random process x of t, and for this random process x of t of the random variable x1. So here the x1 is represented like this. Just wait. Like this, x of t1, right? x1 is equated with x of t1, and now this is the formula to calculate the distribution function of a random process x of t, right? You see, which is very similar to our distribution function which we had seen in the first unit, right? And now this is the case for only one random variable. For example, if you extend this distribution function to two random variables, how the equation is going to be look like this. Just wait, I will show you the equation. And now this is the equation to calculate the distribution function for two random variables. So what are the two random variables here? x1 is a random variable and x2 is a random variable 2, right? So now this t1 is related to x1 and this t2 is related to x2. And all of you observe here, the event should be taken like this for x1, and here also in a similar manner the event of the function x of t2 is less than or equal to x2. So this is the case for two random variables, and if you extend the discussion for n random variable, how the equation is going to be look like this. Just wait, I will show you the equation. And now see, this is the equation for a distribution function of n random processes. So here the n random processes are represented like this. This is x1 and this is xn. So that is x1 to xn we have. So for time consideration, here we are going to consider t1 for x1 and xn for tn, right? For x2 we have t2, for x3 we have t3, like that we have xn to tn, right? And as we had seen in the two variable case, the events are also equated like this. That is, x of t1 is less than or equal to small x1. And if you are going to consider the second one, that is x of t2 is less than or equal to small x2, and so on. If you are going to consider the nth random process, it should be written like this, right? That is capital X of Tn less than or equal to small xn. Okay, so this is nothing but the equation to calculate the nth random process. And what we are finding here, we are finding the distribution function of random process by using these equations, right? Okay, so by using the above three relationships, that is, in the first case we had observed for it one random process, and in the second case we had observed the equation for two random variable case, and in the third case we are going to observe the equation for n number of random process. So see, all of you see here, so this is nothing but the first order density function. This is nothing but the first order density function of a random process. So simply this is nothing but the derivation of the first order distribution function, right? So see here, so this is nothing but that is capital Fx of x1 comma t1. This is nothing but the distribution function, and here we are going to calculate the density function from this distribution function, right? So just simply the derivative of the first order distribution function is going to give us the first order joint density function. So here the joint is nothing but in between these two variables, that is time and the variable x1. As we know that the random process is a combination of two variables. The first one is nothing but x1, and the second one, that is nothing but time. So which we are going to simply treat this x as a sample space, right? So next, we would like to see the second order density function. How we are going to calculate the second order density function. So now observe the second order density function. So second order in the sense here we are considering two random processes, that is x1 and x2. So for this x2, for this x2 we have t2, and for this t1 we have x, right? And observe here, this is nothing but d square of the second order, okay, of the second order distribution function. And now observe here the denominator, that is dou x1 by dou x. So if you perform the second order differentiation of the distribution function of two variable random process, then you are going to get the second order joint density function, right? And if you extend the discussion up to nth order joint density function, the equation will be look like this. Just wait, I will show you. Okay. So this is the equation of the density function of n random processes, represented as x1, x2, and so on, xn. So these are nothing but the random process, and for these random process, we have the equal time slots. That is, x1 is for t1, and if we are going to consider x2, then we are going to consider t2 here in terms of time. And for this nth process, we have tn, right? So observe here the power of differentiation here. What is the power here? N is the power here. And for this nth order distribution function, if you derive it for n number of times, then we are going to calculate the nth order joint density function. Okay, is it clear? Now we would like to move over another concept, that is statistical independence. So statistical independence is nothing but if you consider two random processes x of t and y of t. So in order to prove these two random processes are statistically independent, then we have to show that the random variable group, that is, we are going to consider the x, then x of t1, x of t2, and so on, x of tn is independent of the group of y of t, y of t2, and so on, y of tm. So the basic equation will be look like this. Just wait, I will show this equation, right? So now see here. So this is nothing but a x function, that is x1, x2, and so on, xn. And from here to here, this is nothing but a y function, right? So in x's, we are going to consider n for our representation. Okay, right? And next, for y's, we are going to consider m. M is the notation in y's. And all of you observe here also, we have t1 dash, t2 dash, and so on, tm dash, right? So if the function is like this, and if you realize this joint density function in terms of x and in terms of y. So now observe the equation here. What it is going to tell us here, the two variables are the two random processes x of t and y of t, both are together. And here, if you like to replace this equation by using these equations, which is very similar to the marginal distributions of x and y, then these two random processes, x of t and y of t, are going to be say that they are statistically independent. That is, in order to know the meaning of the statistical independence, in the sense x is not going to depend on y, and y is not going to depend on x. So that is the meaning of statistical independence. Even though in the basic function we have both x and y, but here there is no dependency. So observe the equation from this point to this point. So there is a individual function of x, and there is an individual function of y also. So there is no dependency here. That's why these two are called as statistically independent. And then now we are moving to the next topic, that is first order stationary processes. See, what do you mean by first order stationary process? Now, if you consider a random process, and if it is to be a first order stationary process, then the first order density function does not change with change in time. Then it is going to be treated as first order stationary process. I am repeating again, a random process is called a stationary random process of order 1. Okay, when its first order density function does not change with a shift in time origin, then it is going to be treated as a first order stationary process. And the equation to represent the first order stationary process is like this, that is fx of x1 comma t1. So this is t1 and this is x1, right? And now observe here. So here is x1 is there, and here we are going to observe the term delta. So this is added to time here. That's why here we are going to say that it is a time function, right? Now, what is the condition here? Here the condition is nothing but the random process density function does not change with the time, right? So see, if it is a first order stationary process, then it must be true for any t1 and any real number delta. So this delta is nothing but any real number, and it does not change with the time. Then this one, that is fx of x1 comma t1, is going to be treated as first order stationary process, right? So if you are going to consider this first order stationary process, it is independent of time. That is fx of x1 comma t1 is independent of time. So what is the time represented here? T1 is the time represented here, right? And the process mean value is a constant one. The process mean value is a constant one. And just wait, I will show you with an tick and see, this is the mean value of the random process x of t, right? So expected value of x of t is equal to x bar, which is going to be treated as a constant here, right? And this is the general notation. And if you find the mean values of the random variables, x1 is equal to x of t1, then the equation should be like this. So this is for the random variable x1. So this is nothing but a x1. And if you find out the mean value of this x1, then it is going to be represented with this value. E of x1 is equal to E of x of t1. This is nothing but our random process within the limits minus infinity to infinity. Observe the limits here and here. So that is x1 into fx of x1 comma t1, right? and this one is nothing but which is related to this dx, right? So if you are going to consider the same one for the variable x2, then we have to replace these ones with 2. Here we have 1, and here also we have 1, and here also we have 1, 1, because here we are calculating the equation for x1. And if you are going to consider the random variable 2, simply we are going to replace the notation 1 with 2. Just wait, I will show you. So see, this is the equation for the second variable x2. So this is nothing but the expected value of the random variable x2, and similarly the representation will be look like this. That is v of x of t2, and limits also very similar to the previous equation, and here also notation is also similar to this one up to now. But observe the change here. We have t2 for what? For x1 we are considering the second time instant t2, and now see here there is only dx1, right? So if you are mentioning in the x1 in the equation, that's why here we are going to use this dx1, right? And see what is the significance of t2 here. There is no significance of t2 here. That's why here we are able to say that this first order density function is independent of time, whether it may be t2 or t1 or t3 and so on, tn also. That's not a matter. But we are not doing any derivative furtherly. So simply, if you want to calculate for the random variable x of t2, we have to mention here as dx2. But we are not doing here in this case. We are using only dx1 because this is a first order stationary process. And now by substituting t2 is equal to t1 plus delta, right? t2 is equal to t1 plus delta. In this equation, what happens, we will see now. Just wait, I will show the equation. So see, this is happens when we replace this t2 value with t1 plus delta, right? So see, here we are going to consider only x of t. So this is going to be tell us that here this first order density function is independent of time, and it must be a constant because t1 and delta are arbitrary, right? So this is regarding the first order stationary process, and now we will move to second order stationary process. Second order stationary process. So a process is called a second order stationary process if its second order density function satisfies this equation, that is small fx of x1, x2, and for this x1 we have t1, and for this x2 we have t2, right? And for the same consideration, the realization should be like this. That is, observe the RHS here. So while we are going to consider the T1, that we are going to use T1 plus delta. And for this T2 also, we are adding delta, right? So what is delta? We had discussed previously, right? So it is independent of time and it should satisfy this condition for all T1, T2, and delta. As we know that these time constraints, that is T1, T2, and delta are arbitrary, right? So this is the equation. And see here, this is second order stationary process is a function of time differences. So what are the two time constants here? We have two time constants, that is T1 and T2. And if you would like to maintain the difference, that is T2 minus T1. And this is not a absolute time function, right? Let us remember this point very carefully. A second order stationary process is also its autocorrelation function depends on only time differences, but not on absolute time, right? And now we would like to see the condition for second order stationary process, right? So if a second order stationary process is going to be maintained like this, that is, its autocorrelation function depends on only time differences, but not on absolute time. So see here, these are the time constants. That is, delta is going to be added with the T1 here, and here the delta is going to be added with the T2 here. Right? There is no dependency on absolute time. Right? But it is going to depends on only the time differences, that is T2 minus T1. If the autocorrelation function of this second order stationary process is like this, then only it is going to be treated as second order stationary process, right? So if x1 and x2 are two random variables of a random process defined by x of t at times t1 and t2, then what is the autocorrelation function for this consideration? What is the consideration here? We are considering two random variables x1 and x2 for a random process x of t. These two random variables are defined at the time intervals t1 and t2. Then the autocorrelation function is given by the formula. Just wait, I will show you the formula. Okay, so see, this is the formula for our conservation. I am telling the conservation once again. Here we are considering two random variables, x1 and x2, for a random process x of t defined at two time intervals, right? So see, t1, t2. And here the autocorrelation function is defined as the expected value of the random process x of t1 and x of t2, right? Now, if you replace the time difference as tau, if you replace the time difference as tau, previously we told that what is the time difference in the sense the time difference is nothing but t2 minus t1, then the equation should be like this. If you put tau equal to t2 minus t1 like this, then we are going to see the equation, that is the autocorrelation equation Rxx of t1 comma t1 plus tau, which is equal to expected value of x of t1 and x of t1 plus tau. That is simply we are going to represent with rxx of tau, right? So see here, what are the constraints here we are considering? These ones are applicable to here, that is t1 is applicable to this t1, and here the t1 plus tau is going to be applicable to this x of t1 plus tau, and simply we are going to represent this function with rxx of tau. This should be like this, right? So this is about autocorrelation function, and now we would like to move to wide sense stationary process, right? Wide sense stationary process is a random process x of t, right? When it is going to be set told as wide sense stationary process. Okay, so this wide sense stationary process is also called as weak sense stationary process of x. Just wait, I will show you with the equation. So now see, these two are the conditions to be a process to be wide sense stationary processes, right? So that is here the random process is x of t. That is the expected value of this the random process x of t is going to be equal with x bar, and which is going to give us a constant value, right? And see, this is nothing but the autocorrelation function of two random variables, which we had seen previously for the consideration of two random variables x1 and x2. They are defined at two time intervals t1 and t2 of a random process x of t. So simply here, this wide sense stationary process is nothing but a random process x of t of second order stationary process. Okay, if it satisfies these two conditions, that is the mean of the random process is going to be considered as a constant value, and the autocorrelation function is independent of absolute time. And I'm going to repeat this point once again. This is also discussed in the previous concept. That is, in the second order stationary process also, we had considered the same discussion. And now I am going to explain you once again. See, this is nothing but here we are going to consider the two random variables, x1 and x2 of a random process x of t at two time intervals. Then this is the formula to calculate the autocorrelation function of those two random variables, right? So by seeing these two conditions, we are going to conclude that this wide sense stationary process is also a second order process, but it should be satisfy these two conditions. What are the two conditions here? The first condition is nothing but the expected value of this random process should be a constant value, and the autocorrelation function of the random process is independent of absolute time, right? So this is about wide sense stationary process. Now we would like to move to jointly wide sense stationary process. First of all, consider two random processes x of t and y of t. So if they are jointly wide sense stationary, then the cross correlation function of x of t and y of t is a function of time differences. As we know that what is meant by time differences? Time differences is nothing but that is we are going to equate the tau to t2 minus t1, right? And see here the cross correlation function of x of t and y of t is a function of time differences, but not going to depends on absolute time. Then the cross correlation function is given by this formula, that is Rxy of t1 comma t2 is equal to expected value of x of t1 into y of t2. So if you place the time differences, that is tau equal to t2 minus t1 and t equal to t1, then the cross correlation function, that is Rxy. This is nothing but the cross correlation function representation. That is Rxy will become look like this, right? Rxy t1 comma t1 plus tau is equal to expected value of x of t and y of t plus tau, which is going to be equated with this Rxy of tau. And now we would like to see the conditions for joint wide sense stationary processes. Just wait, I will show you the conditions by the mathematics. So see, these are mathematical relations or mathematical conditions. A process should be satisfied in order to call it as a jointly wide sense stationary processes. That is, sorry, this is not clearly visible, but don't worry, I would like to explain it. So E of x of t is equal to x bar, which is going to be treated as a constant. So this condition we have discussed for both second order and as well as first order stationary process also. And the second variable, that is y of t, right? Y of t is also y bar. That is the expected value of the random process. Y of t is also a constant value. And this is nothing but the last equation, that is the equation of cross correlation by replacing the time differences. That is expected value of x of t and y of t plus tau is equal to Rxy of tau. So by seeing this, the third condition, here the cross correlation function should also independent of time, but it is going to be depend on time differences only. Just wait, I will show you this cross correlation function more clearly. So the third condition is also very similar to this one. This one is nothing but what is here? See here, this is the expected value of x of t into y of t plus tau, which can be treated as a cross correlation function, right? Now we would like to move to strict sense stationary processes, right? So a random process x of t is to be a strict sense stationary process if its nth order joint density function does not change with the time or shift in the time value, right? For all time factors, that is t1, t2, and so on, tn, And the second arbitrary that we are going to consider here is delta t, right? Just wait, I will show you the mathematical representation of a strict sense stationary process. So see here, so this is nothing but the mathematical representation of the strict sense stationary process. So see, here we have x1, x2, and so on, xn. So here for x1 we have t1, for x2 we have t2, and for xn we have tn, right? So it should be independent of absolute time. So here the absolute times are represented with the t1 plus delta t and t2 plus delta t and so on, tn of delta t, right? So now we have to remember 3 points regarding this strict sense stationary process. That is, if a process is stationary to all orders, that is for n equal to 1, 2, 3 and so on, n, then it is called as strict sense stationary process. And this strict sense stationary process is also called as nth order stationary process or stationary to order n, right? The third consideration we have to remember here, the strict sense stationary process is also a wide sense stationary process, but the converse is not true for all cases, right? If the stationary conditions of a random process x of t does not hold for all n, but holds for n less than or equal to k, then the process x of t is stationary to order k or kth order stationary process. So this is nothing but how many number of values we are going to see the process should be independent of time, then it is going to be treated that order. For example, if a random process x of t, okay, holds up to like the number 6, then it is going to be treated as 6th order stationary process, right? So this is about processes of random process. First, we have discussed about in this lecture. Firstly, we have discussed about distribution and density functions of random process for one process and for two processes and for nth order process also, followed by statistical independence, thereafter followed by first order stationary process and second order stationary process, and the third one wide sense stationary process, and the fourth one strict sense stationary process. Meanwhile, while we are discussing here, we had observed cross correlation function and auto correlation function, right? What are the conditions to be autocorrelation function and cross correlation function, right? So this is about today's lecture. Have a nice day. Thank you.